In this class, we are going to see definition of group. In the previous lectures, we have already seen what is a function and what is a binary operation. So, given a non-empty set G together with binary operation star, it will be called as a group if some properties are satisfied. Now the question is, what are that properties? So first property is associativity, the second property is existence of identity, and the third property is existence of inverses. Now let us try to understand this with the help of examples. Remember, if we want to understand the definition, we should try to construct the examples. So let us see few examples. Now the requirements are, we should have a non-empty set together with binary operation, and then we can verify the following properties. Let us say we are having set of integers. We already know that plus is a binary operation on that. Now let us try to verify all the properties, all the three properties in fact. Now suppose I take three numbers from Z, let us say 2, 3 and 5. Now what is the associative property saying? Whenever you have three numbers, if you operate first two numbers first, I mean if you calculate A star B first and then take its star with C, whatever answer you get, that should be exactly same as finding B star C first and then finding A star B star C. For example, in this case our binary operation is plus, so either we find 2 plus 3 first or we find 5 plus 3 first. The answer should remain same, and if this happens for any three elements of the given set, then that set will satisfy the associative property. So here, as we can observe, if we add 2 plus 3 first, then the answer that we are going to get is 5, right? Plus 5, that is going to be 10. Now if I add 3 plus 5 first, then this will be equal to 2 plus 8, that is also 10. So it implies that these three elements of Z satisfies the associative property. But if we think deeply, if we take any three elements of Z, still it will be satisfied, right? So if I call the elements as M, N and L, right? So if you add first M plus N and then add it to L, or firstly you find N plus L and then add it to M, still you are going to get exactly the same answer, and therefore the associative property is satisfied by integers. Now talking about the next property, what should happen is we should be able to find an element in G such that A star E should be equal to A, that should be equal to E star A for all A belongs to G. Now in our case, star is plus, so our property will be A plus E should be A, this should be equal to E plus A for all A belongs to Z, because our set G is Z. So we are trying to think of some element that should give us 5 back, that should be again equal to some element plus 5. Here I am taking a particular case so that it is easier to understand than we can generalize. So can you guess which is that element? 5 plus what is equal to 5? That's exactly 0, right? So if you add 0 in 5, we'll get 5, and this is further equal to 0 plus 5. But remember, this element should be a member of what? G. In our case, it should be a member of Z. Is 0 a member of Z? Absolutely yes. Therefore, there exists 0 belongs to Z such that if you take any element of Z, let us call it as m. So m plus 0 comes out to be m, which is equal to 0 plus m for all m belongs to Z. Thus, identity element exists in Z. Now the next property is existence of inverses. So what should happen is, for each A belongs to G, there should exist A inverse belongs to G such that A star A inverse should be E, that is equal to A inverse star A. Now let us convert this property in our problem, right? So in our case, G is nothing but Z. So for each A belongs to Z, we should be able to find such an element. Direct this means what? We have to find. So we should be able to find such an element A inverse belongs to Z such that A plus A inverse should be equal to what? Remember, our identity element is 0. So A plus A inverse should be equal to 0, that should be equal to A inverse plus A again. Let us try to understand it by taking a particular example. So if I take my element of Z to be 5, so 5 plus which element will be equal to 0, that element we have to find. So can you guess what is that element? Yes, that element is minus 5, and that is further equal to minus 5 plus 5 as well. So in this case, we say that 5 inverse is nothing but what? Minus 5. And in fact, we say that minus 5 inverse is nothing but what? 5. Now this is for a particular case. Can we generalize it? Let us say if we have m as an element of Z. So after adding which element in m, we are going to get 0. That's minus m, right? Absolutely. So therefore, m plus minus m is actually equal to 0, which is equal to minus m plus m. Therefore, what is happening? Each element in Z is having an inverse as well, and therefore Z with respect to binary operation addition is actually a group. Now there is one more concept in group theory, that is nothing but of abelian groups. Now the question is, what is the condition? So the condition says if A star B is equal to B star A for any two elements of that set G, then the set G star will be called as abelian group. Now the question is, does this property satisfy in our case? So if we take two elements of Z, for example 5 and 8, so what is 5 plus 8? That is 13, right? And what is 8 plus 5? That is also 13. If you interchange the roles of the elements, still, I mean the positions, still you should get the same answer. Now if you take some another example, let us say minus 5 plus 10. So what is minus 5 plus 10? It is 5. And what is 10 plus minus 5? It is also 5. So it can happen, actually it happens for any two elements of the Z, right? So therefore, what do we have? We can say m plus n is actually equal to n plus m for all mn belongs to Z, and therefore Z is actually a abelian group. Now the same thing can be generalized to the set of rationals, to the set of reals, as well as to the set of complex numbers.